We're very delighted to have Mildred Dresselhaus as our first speaker to open this session. She's going to be giving a historical perspective of carbon nanomaterials. I'll open up with Millie just won the Kavli Prize, a very prestigious award, and I'm sure she's going to touch on that as well. So take it away.
Okay, thank you very much for inviting me to talk about nanocarbons, one of my favorite subjects, of course. And the very first view graph shows me about 50 years ago. Before I started working on carbon, I was working on superconductivity in that picture. And on the right, I guess, was at the time I had already worked for some years on nanocarbons. And I will tell you in my summary today about some of the things that we found and what we're working on today. So the citation of my award was for basically electrons and phonons, but also the electron-phonon interaction. And while it's true I worked on some of that, some of the specifics in what was cited, I haven't really finished by any means. So this is where I'm working today, is putting together what I've done with electrons and phonons and working with my many collaborators on trying to make progress in this field. So when I started working on carbon in 1960, as you can see by this picture, this is number of publications on the y-axis. This was a very, very silent field. There weren't very many people interested in carbon. And people used to ask me, why are you working on this? Isn't that very silly? It's such a complicated thing. But over the years, many people have joined the crowd and have seen the beauty in this nanocarbon field. So in the 1970s, I started working on intercalation compounds. Of course, at that time, it was bulk. I worked in that field for about 15 years. And but, you know, Fullerenes came along and nanotubes. Now it's graphene. But I'm not going to cover it, say anything about graphene because when I wrote the abstract, I only talked about nanotubes. So I ended my story there, although we're working on many other things today. So I was very attracted by the linear E versus K. And many other people in this audience were also attracted to graphene for that reason. At that time, everything was semiconductors, and semiconductors normally have quadratic E versus K. But luckily for me, in 1960, when I started in this field, my contemporary, Joel McClure, we went to graduate school together, so we knew each other very well. He had worked out by that time the energy levels of graphite in a magnetic field, and that was where I started my work, because we were studying, as you can see in the next view graph, with magnetoreflection, the transitions between quantized states produced by a magnetic field in the valence band to the conduction band. And we did many experiments that measured the parameters, basic parameters of the graphite band structure during those years in the 1960s. But the most important experiment that we did was the very first experiment with polarized light, circularly polarized light with a laser. And the laser that we used was produced especially for this experiment by Ollie Javan, who was the inventor of the CW laser. And together we were able to show with the circularly polarized light which bands had to do with electrons and which ones had to do with holes, and this established the location in the Brouillon zone for electrons and holes that you people use today. This is an important experiment because before that time, the assignment of electrons and holes was backwards from what it is today. In the 1970s, we entered the world of intercalation compounds. I was introduced to that when I gave a talk in the 1960s at Bell Labs, which was a premier research lab at that time, better than any university around the world. And when I was there talking about graphite, they told me or encouraged me to start working on intercalation compounds. And the first paper that we did was on the order of 1973. It took me a little while to get into it because we couldn't really figure out what was the right thing to measure. But anyway, we measured many things, including magneto-optics, transport, optical properties, many things, and worked in this field just about until high TC came along in the mid-1980s, and then students didn't want to work on intercalation compounds anymore. They wanted to work on high TC. So we moved along. But in that work, there were a couple of things that I note for you that were important. For one thing, we found that the stage 1 compounds, like C8 rubidium, shown on the top, behave rather differently from stage 2. Now, stage 1 compound has just a single layer of graphene that's on either side of it has intercalate. Stage 2, there are 2 layers of graphene that are together, so that's sort of like a bilayer. And at stage 3, C36 rubidium has a trilayers, so maybe you have ABA stacking. So, and you could see that 2 and 3 layers are not too different from each other, but one layer is very different, and that topic took quite a bit of our time in the early days. Of course, we couldn't make just few layers like today, and that's why I found that the work on very few layer intercalation very interesting. I've known this for some time, but I think it has real potential for answering many issues. We also studied the modification of the intercalant, and if you put a molecule inside intercalation compound, the normal vibrational frequencies change by a great deal. For example, bromine changes by almost 50%. So that's a huge, huge change. And I'm not sure that there are many issues about this particular intercalation that never were answered properly for me. So maybe the folks now doing few layer graphene can shed some light on some of these old issues that have been around for 30, 40, 50 years. Well, at the same time in the 1980s, we started ablating graphite. And by doing this, we found that the chunks of carbon that came off were much larger than we expected. We thought, but when we had a laser hitting graphite surface, that would be C2, C3, just little tiny chunks, but it wasn't that. And the reason that we knew it wasn't, there were 2 reasons. One was an obvious one. Our clothes got very dirty. They got all sooty. So it wasn't very tiny clusters. But the other thing was that the amount of graphite that was consumed was very large for the small amount of energy that we put in. So that told us that much of the carbon didn't break up. It stayed together as large clusters. And we didn't understand that, so I went to talk to the folks at Exxon Research Lab. They were the big experts on clusters of carbon at that time. And they had gotten up to clusters of size 15. And I told them size 15 just won't do it. We need something C100. We need something much bigger than C15. And so they did an experiment to look for higher clusters, and that's the famous trace, the ion signal versus cluster size. That's well known to many of you because that was the beginning of Fullerene discovery. So there's a big peak at C60, another peak that's a little bit smaller at C70, and those are the molecules that we call fullerenes today. Of course, Kroto, Smalley, and Curl made the proper identification, and that launches into the whole work on fullerenes. But it was one of these things that when I was invited to talk about our work, people wanted me to write up something about fullerenes. They should have asked Smalley, but he wasn't writing. He told me to write. So we wrote a book. But our book was mostly on spectroscopy. And so this is sort of the sort of thing that we were working on. So the top is not very high resolution. You could see the famous spectrum on the top that was discovered at the time of Smalley's first work in 1985. But the lower figure shows something 200 or so transitions. And when you work out all the group theory that you could have through second order, you come out, because of the high symmetry, with about 200 allowed transitions, and you see each and every one of them. And it was kind of the most amazing thing about molecular spectroscopy in the solid state that I'd ever encountered in my career. So that was really a lot of fun. I was teaching a course in group theory in 1984, and so we were fantasizing about the regular icosahedron. So the class worked out the whole thing for hydrogen atoms, and they were awfully angry with me because I didn't give it to them in carbon. So, well, I see this preceded by 1 year, so I didn't know that it was going to be discovered. Okay, in 1998 there was a change in my whole career because the magnet lab disappeared, and all the experiments that we used to do at high magnetic field couldn't be done readily. The lab moved to Florida, and I was still at MIT, so that wasn't too close. So we changed fields, and well, for the young people in the audience, sometimes in your career when you have discontinuities like that, that's the best thing that ever happened to you, because I would say that my banner year of all 50 or so years that I'm recording here, 55 maybe closer, that was a banner year for me for the following reasons, as you'll hear in a moment. So anyway, before that year started, we were doing this fast optics, and we were doing this with Eric Ippen, who was very prominent in fast optics, and so we collaborated. And this is the first work on the impulsive excitation, producing this long train pulse of vibrations. And so we did this in all the narrow gap semiconductors because I thought it would be good, and it was amazing. The best one was C60, but I couldn't find my reference on that, so you see this one. Anyhow, at the same time, we were working on carbon fibers, and that all started through a meeting endo at an Intercalation conference, the second one, which was held at Provincetown, and he came as a very young researcher. This is Morinobu Endo in Japan, and he introduced me to graphite fibers, and we've been working together now for 40 years or so, writing many papers. But I was into fibers, and we wrote another book. So this is a book on carbon fibers. And I was invited to give a talk about carbon fibers in Washington, and at the same conference, the other invited speaker was Rick Smalley, and he was invited to talk on C60. And then at the end of the conference, or toward the end of the conference, they brought the two of us up on the stage, and somebody in the audience asked, what is there in common between carbon fibers and C60? So, well, it's pretty obvious what's in common. So if you look here at the picture, you can see that here's C60, and carbon fiber is something big. And so you go C60, C70, 80, 100, 200, and it gets longer and longer and longer, but it's always single wall. So maybe you can make something that's like that. So we had the idea, and that fall, two young gentlemen came to visit, and shown over here, Saito and Fujita. And somehow they wound up in my office. They didn't actually know each other, but they met and decided to help me figure out if you could make a single wall nanotube, would this be an interesting thing? Was it worth trying to make? And so we came up with the idea, or they came up with the idea. That was really their work, but I could understand quite readily. So we take a graphene sheet like this and we roll it up to make a cylinder, and when that happens, instead of having an infinite number of atoms in the x and y direction of the plane, you have only a very small number to make this ring here. So maybe it's only 10, and that tells you that you have 10 cutting lines on these cones, the Dirac cones. That means you only have 10 cutting lines where you have real quantum states. And in that case, if a cutting line goes through the center, goes through the apex of the cone, then we would have a metallic case, because then the valence and conduction bands would touch. There would be no band gap. But if that didn't happen, you'd have a semiconductor. So the prediction in our paper in 1992 was that these weird things, these single-wall nanotubes, would have the property, depending on the orientation of the hexagons, they would either be metallic or semiconducting. Well, that was kind of an interesting idea. People didn't believe it, but it turned out even to be correct. And it sort of launched the field. Now, the interesting thing about the low-dimensional density of states that you could see here, so this is one-dimensional density of states, it has spikes. And that means that you have a very, very high density of states possible. That means that you can have a huge enhancement of any optical signal that depends on matrix elements. So, and that, when we eventually saw the first Raman spectra, we had to have a pretty good sample. The original work was done in 1994. It was done 3 years before this paper was published. And it was done in a sample that had 1% of nanotubes. And the signal that we got was so large and different from anything else that I knew that if we worked hard to make a good sample, that this was going to be a good experiment. And when we finally got a good sample, was provided by Rick Smalley, we got this spectrum. It's kind of a historic spectrum, 1997 paper of Rao, Eklund, and members of our group. Smalley was there too, because he gave us the sample. It was a remarkable spectrum, because you see that the G band, where the two nearest neighbor carbon atoms are vibrating in optical motion, it differs so much from one laser energy to another. So that gave us immediate confirmation that this was a resonant process with a large enhancement factor. And then we also found the radial breathing mode with its inverse dependence on diameter, which gave us a characterization of the nanotubes that were made. When we actually did the spectrum, as you can see on the right, the early spectra were done on bundled samples, so we had mixtures of metallic and semiconducting tubes. But later, we figured out a way to that we could study individual nanotubes. And by doing that, we could actually identify the N and M, so we can get the chirality of the tubes at the same time. So that launched single nanotube spectroscopy of all sorts, optical properties of that ilk. And you could see on the right spectra taken on individual tubes. And that's kind of what we've been doing ever since. So when we do spectroscopy on these low-dimensional carbon systems, we do ensembles to begin with, because that gives us the lay of the land, so to speak. And then we individualize and just do the individual ones, because one is very different from another. And I'll show you a little bit more about what we're doing on that for the rest of the talk. So here's double-wall nanotubes. At the talks in this session W, you've heard about nanotubes, but perhaps more on graphene, and you've heard about misaligned stacked layers. So when you have two layers and they're not stacked exactly one on top of another, then you have some misalignment angle. And if you have a misalignment angle, you have something that looks like this. You have a turbostratic case, and you get a spectrum that's gives information about that. On a flat plane, as you move the two layers one from another, it doesn't matter too much where the location is for a turbostratic layer. And even when you have them mostly aligned and you have one point aligned and then you make some rotations, if you go 30 degrees, 60 degrees, you get some interesting patterns. And then we have theories about what happens when you do small misalignments. Double-walled nanotubes, because of the metallicity, they can have 4 flavors, as you could see over here. They can be metal and semiconducting in any combination. And so the properties of each of them are quite different one from another. And this is still an area where there's a lot of room for more experimentation. The number of papers in this field is pretty limited at this point. We know something about it, but this system is kind of interesting because if you move a tube inside another, then you change the orientation to some degree. And that's worth studying. Here's the way the tubes look. Made by Endo Sensei. This is our collaborator going back to 1980 that I mentioned earlier. We still work together. And one of the interesting experiments that we've done recently is an experiment where we take the same inner tube, call it a 6-5 tube. That's not the only one we've done, but that's a common one. And so it should have a certain chirality, 6-5, and that tells you it has a certain diameter, and you expect that you'd get the same Raman frequency for the radial breathing mode. And to some degree that's true, but it's that frequency and line shape and all that stuff is slightly different from one sample to another, and that the reason for that is that there's a small misalignment angle between the two tubes. And even when if you would escalate one inside the other, move it inside, you get a different local pattern, and that gives you some difference in the spectra. And so we have 3 groups shown there, and what that's supposed to indicate is that we have some patterns that are very similar, where we have the same tube, and maybe even the same outer tube, but the orientation between the hexagons and the tubes are a little different as we move along, and we get a different spectrum. So this makes an interesting situation, and work on this is still in progress, and there are almost no groups working on it, so it's an area where there's still possibility. And I think now we're ready to begin to understand this much better with the work on misaligned graphene. So the different parts of nanocarbons help one another in giving information that's useful from one area, like graphene, to something a little bit more complicated, like a nanotube. This is a little bit busy slide, but this is done on double-walled nanotubes. And depending on what the energy range, a laser excitation energy range, the way we do the experiments is like we like to use something like Thai sapphire laser, where we can have a whole series of laser frequencies that are very close to one another, so that allows us to do profiles of the signal as we change by very little bit. So we can do the whole line shape of the profile, the excitation, peak in excitation energy, peak in intensity as we change the excitation energy. And data is shown here for what happens to the G-band for some different tubes. And you can see that it's different as we move across laser excitation energies. So this allows us to be in resonance with the inner tube and then the outer tube in the double wall, and to get information of the line shape of each of them. So that's what this view graph is about. So I've told you a little bit about individual tubes, I've told you something about bundles, and I've told you something about the connection with graphene and how we relate results from one to another. Our latest interest is working with 3 walls now, so we have triple-walled nanotubes. And so that corresponds to graphene with 3 layers. And we know that we can have ABA stacking, we could have ABC stacking, which is rhombohedral stacking, and then we can have turbostratic stacking. And they all give different spectra, and they all have their analogies with carbon nanotubes. So here you could see on your left, double wall, and then the next picture is triple wall, and you could see very clearly 2 walls and 3 walls. And sometimes we're lucky and we can get lots of information with a single laser, as we show here with triple wall. And this is done with an ensemble, so we have inner walls for many, many different tubes, and they're different. But then if we single in on an individual tube, and I'll show you later, then we can look at each of the walls independently. So here's some wall. This is a thesis, very recent, of Thomas Hirschman. He works for Cornelius Nielsch, and I'm a kibitzer on this thesis. I'm a reader. So we've been working together to study triple wall nanotubes, and he got some really interesting results. So depending on the range of laser excitation energy, this is a nice view graph because it shows you on your right-hand side of the Katara plot, there's a range where we have the inner walls, and that's sort of bluish. And then we have a range to the left, which is red and green. And in that range, we have the middle wall, the triple wall nanotube, and then the outside has a very low RBM frequency that's not shown on this view graph. But you could see that for the innermost walls, that's shown on the right-hand side over here, that it makes quite a difference whether we have semiconducting tubes in the inner walls, those are the red ones, or we have metallic tubes, those are the bluish ones, that the frequencies are different, so that the metallicity changes, and the distance between the walls is different too, so that there's an interaction between the tubes that gives information about the metallicities. So we have a formula that's taken actually from individual tubes, and that's shown on the upper right. And that formula, it depends on a correction term that involves the C, capital C sub E times dt squared. That's the diameter, tube diameters. And that value of C is different for semiconducting and metallic tubes, and we have actual values for that. So that's very new. We haven't had that before, and shown the difference between the metallic and the semiconducting tubes, and it shows up on the plot that's shown on your lower left, right. Well, in this experiment, this master's thesis, which is really an outstanding master's thesis, he was able to find a few tubes, triple wall tubes that we could study individually, and the spectra are shown here. And from those tubes, you could see on the right-hand side, on the rightmost side, the areas where we take a given tube and we run it through neighboring frequencies to get the excitation profiles. And you can see that the excitation profiles look somewhat differently as we move up in energy, as new peaks come in. So in my talk today, I've gone through sort of 50 years. I don't know if that was my assignment for the organizers, but I've been in this field I started in 1960, so I guess it's 52 years. I'm finishing 52 and a half years, something like that. And so we've taken you through graphite, three-dimensional material, through intercalation compounds, where our first effort to look at individual layers, but we couldn't see them isolated back in the 1970s, not like we can today. Going through fullerenes, nanotubes, and finally graphene. I only had a few comments on graphene. But the message I would like to leave you is that this field might be old, but it has new wrinkles. When I come to a talk and a session like W, and I heard a paper on intercalation compounds, doing work that was similar to what we did 40 years ago. But it's different because now you can have just a few layers and you can look at individual ones. You have all these new tools, and there are many possibilities now that weren't available at that time. What amazed me is that the person that was working on this few-layer graphene with modern techniques, he told me that most of the things that we wrote about in ancient times actually turned out to be more or less correct. Well, we're always surprised when that happens, but from my side, listening to what he had to say, when people return to some of these old issues that we sort of knew about before, but there were many gaps because we couldn't get it to the bottom of things. We didn't know how to make samples the way people know how to make them today. We didn't know how to characterize the samples. And we didn't know about the science as well as we do today. And maybe we didn't even ask some of the important questions because they weren't on the horizon. So saying all those things, I would say that for some of you that like history, and this is supposed to be a historical talk, you can go back in the old literature and I'm sure you'll find many topics, I don't know how many, but there are many of them out there, like intercalation compounds, for example, that have many issues that were not explained in the early days, the first pass. We just didn't have the tools to do that. And amazingly enough, those issues haven't been explained yet. So, problems for the young people in the audience. New discovery for you. I end at that point. Thank you.